Hello, I'm Cherry and I'm about to discuss a very interesting research published in the Journal of Geophysical Research in August 2020, and that is how sediment thickness influences subduction dynamics and seismicity. We have all heard about earthquakes and the destruction it causes. Megathrust earthquakes are the earthquakes which occur at subduction zone. The world's largest earthquakes are generally associated with interplate slip along the subduction megathrust. It has long been recognized that sediments subducting along the megathrust influence the occurrence of these earthquakes. However, the limited observation span and the concurrent influence of the multiple parameters on megathrust behavior prevent us from understanding how these sediments affect earthquake size and frequency. This paper addresses these limitations by using two-dimensional viscoelastic plastic seismothermomechanical numerical models to isolate how sediment thickness affects subduction geometry and seismicity. The key points which we will be discussing are: thick sediments reduce slab depth and increase seismogenic zone width and maximum earthquake magnitude. Thick sediments also favor splay over outer rise faulting and partial over complete megathrust ruptures. Simulation of long-term subduction dynamics and sediments significantly increases estimated maximum magnitude of the megathrust. There has been previous researches with leading up to this research. In 1989, Ruff first noticed that the magnitude of megathrust events tends to be larger in sediment-rich margins. In 2018, earthquakes it was established that earthquakes occur in subduction segments with a trend sediment thickness greater than 1 kilometer. It has recently been shown that subduction zones that have produced giant earthquakes tend to have a rather smooth incoming seafloor, implying that the physical and geometrical properties of the plate interface are first order controls on the seismogenic behavior of subduction megathrust. Weakening of megathrust. Subducted sediments also influence the frictional properties of the megathrust. Clay-rich material and ocean floor carbonates are frictionally weak under a variety of conditions. Moreover, the presence of fluids, particularly at high pressure, can weaken the megathrust by reducing the effective normal stress. This is a global map showing the spatial relationship between trend sediment thickness and giant megathrust earthquakes. The red circles here represent the magnitude of megathrust earthquakes, and these lines represent the sediment thickness in increasing order from left to right. Yield strength, that is, the stress at which predetermined amount of permanent deformation occurs, depends on cohesion, friction coefficient, and pore fluid pressure factor. At every Lagrangian marker, mu is calculated as a function of the viscoplastic slip rate, which is as follows. Gamma is the amount of slip rate induced weakening, which is equal to 1 minus static friction divided by dynamic friction. The viscoplastic slip rate is given by this formula, where eta m is equal to local velocity and delta x represent grid size, the Euclidean grid size. This formulation allows for spontaneous localization of the deformation at any orientation, both on and off megathrust. This means that the rupture along the megathrust as well as in outer rise and sedimentary wedge are governed by local stress and strength conditions. For each two-dimensional ruptures, magnitude is estimated using the empirical rupture width magnitude scaling relationship defined for subduction zone earthquakes. Magnitude is equal to 4.04 plus 2.17 log of W, that is the rupture width. This is a 1900 by 200 kilometer square trench normal section. An oceanic plate subducts into the upper mantle beneath a continental plate and accretionary wedge. Subduction is kinematically driven by imposing a constant velocity of 7.5 cm per hour year within a small region of the subducting plate. The upper portion of the model is treated as an internal free space by imposing a 12.5 km layer of sticky air. Free slip boundary conditions are applied at the top and side boundaries of the model, and we impose an open boundary condition at the bottom boundary. The upper portion of the model, as I told you, is the sticky air. The initial temperature of the continental lithosphere nearly increases from B, that is equal to 0 degree centigrade at the surface duties equal to 1300 degree centigrade at 100 per kilometer, that the gradient of the mantle is a diabatic and is said to be 0.5 degree centigrade per kilometer. The temperature field, geometry and mechanical properties of the megathrust are also significantly affected by sediment thickness. Let's first look at the temperature distribution. Here, the dark and light gray shaded areas in panel highlight the location of the seismogenic zone and transition to the up depth and down depth aseismic regions respectively. At T sed is equal to 0, that is when the sediment thickness is equal to 0 kilometers, the up depth and down depth limits are located at 20 kilometer and 60 kilometer depth, whereas for 8 kilometers it is located between 10 kilometers and 46 kilometer depths. Therefore, the depth of the megathrust seismogenic zone decreases distinctly with increasing the sediment thickness. Increasing the sediment thickness on the incoming plate result in a decrease of slab depth as the trench retreats due to the seaward growth of the sedimentary wedge also unbends the slab. Looking at the megathrust geometry, we observe that the slab tip at seismogenic zone depths linearly decreases as a function of T sed, with values ranging from 26 degrees to 8 degrees. This also results show that the down dip width of the seismogenic zone W increases linearly from 81 kilometers to 255 kilometers with increase in the sediment thickness. The decrease in megathrust depth result in a wider seismogenic zone so that the maximum magnitude of megathrust earthquakes increases. And what is the effect on yield strength? As you can see, we measure sigma yield, that is the yield strength, between the 150 degree centigrade and 350 degree centigrade isotherms at the bottom of a sedimentary layer, because this is where megathrust earthquakes preferentially propagate in our models. Results for increasing sediment thickness show that sigma yield is smaller across the entire depth range of the seismogenic zone. This shows that models with thick sediments on the incoming plate have relatively weaker megathrust. Let's see at a particular depth. More is the sediment thickness, less is the stress required for deformation. This implies that megathrust becomes relatively weaker and are more prone to large magnitude earthquakes. Let us now look on role of sediment thickness on short-term and short-term seismic behavior. During the short-term evolution of our models, events propagate on and off megathrust. Megathrust earthquakes nucleate close to the down dip limit of the seismogenic zone, where plate coupling decreases spontaneously due to the brittle ductile transition. The events propagate upward and partially break into the up dip velocity strengthening region. As sediment increases, megathrust becomes steep. More is the slab bending, thereby more outer rise the earthquakes. Of megathrust seismicity is limited to the outer rise region for sediment thickness 0 km. In contrast, for sediment thickness 8 km, outer rise events are absent and off megathrust earthquakes propagate exclusively within the sedimentary wedge. Indeed, the number of earthquakes in the slab bending area, which is this, the number of earthquakes in the slab bending area decreases as a function of sediment thickness, while there is a positive correlation between the number of splay falls within the sedimentary wedge and the sediment thickness. What about the recurrence relation? In the model, as you can see, when the sediment thickness is less than equal to 4 km, the megathrust ruptures are in regular seismic cycles with periodic and quasi-characteristic events that saturate the entire seismogenic zone width. In contrast, for sediment thickness with greater than 6 km, smaller partial ruptures occur in addition to large quasi-characteristic earthquakes. The maximum moment magnitude of megathrust events and Mmax increases linearly from 8.2 to 9.1 as a function of sediment thickness, which is consistent with the first order control of sediment thickness on the seismogenic width. Thus, we can conclude that the amount of sediment does strongly influence megathrust seismicity. As the sediment thickness increases, the megathrust generates events of increasing maximum magnitude, but the time needed for these events to occur also increases. Implications. Subduction segments are often characterized by a shallower interface dip and larger seismogenic zone. Megathrust is on an average weaker for increasing sediment thickness. This is mainly due to shallower seismogenic zone and a lighter forearc structure that decrease pressure and the normal stress acting on the interface. Maximum magnitude of earthquake increases with increasing sediments. Increasing the sediment thickness causes the interpolate seismicity to migrate from outer rise region to the sedimentary wedge. Finally, we concluded that the amount of sediment strongly influences megathrust seismicity. As the sediment thickness increases, the megathrust generates events of increasing maximum magnitude, but the time needed for these events to occur also increases. The recurrence time also increases, and the magnitude also increases. This strengthens how crucial it is to bridge the time scales from tectonic evolution to earthquakes to improve seismic hazard assessment at subduction zones. This paper has been cited in What Controls Maximum Magnitude of Giant Subduction Earthquakes. This research is used to predict maximum magnitudes of subduction earthquakes worldwide, demonstrating the fit to magnitudes of all giant earthquakes of the 20th and 21st centuries and the good agreement with the predictions based on the statistical analysis of observations. Thank you.